Hello, my name is Matthew Dunbrack, and today I will be doing a joint presentation on machine learning methods for anti-neutrino-based safeguards with Jonah Cullen. So for my part of the project, I focused on this retina system, which was basically if you're able to put an anti-neutrino detector next to the core of a reactor, you'll see all these different anti-neutrino counts and energies based off the inventory of that reactor. So theoretically, if an adversary was to pull special nuclear material, such as plutonium, out of the core, you would be able to pick up on it based off the anti-neutrino counts and energies that you're seeing compared to simulations. So for this work, we did a sensitivity study where we tested the absolute limits of this idea on simulated results, and then we also simulated different diversion scenarios, and we were able to basically come out with these predicting powers and safeguards power based off how well a machine learning model can predict that the diversion scenario took place. So for this simulation, we applied it to the AFR 100, which is a small, fast reactor. So it bred plutonium at various locations and assemblies, and we simulated what we were expecting for the anti-neutrino counts, and then we simulated if an adversary was to pull one significant quantity of plutonium from these different assemblies. And then we applied these simulations, and we came up with a high-bias machine learning model using a support vector machine, and we were able to come out to what safeguards power were actually possible in these different scenarios. So from the results, switching from our statistical chi-square approach that we previously used to this new support vector machine model, most of the safeguards power actually increased across the board compared to the statistical approach, and we are also able to test it by basically withholding data from the training of this SVM and then applying it though to the test to see basically how well this model can do for unseen scenarios that it has never seen before, it wasn't trained with. So the impact of this work was we were able to come up with a new methodology for identifying the optimal conditions based off the safeguard power for pulling different plutonium from different assemblies. We were able to come up with which diversion scenarios were more optimal for hiding against the machine learning model. We were also able to collaborate with Lawrence Livermore person, Nathaniel Bowden. For future work, we're going to decrease the computational load, ideally so we can run even more diversion scenarios, and we also hope to extend our MTV collaborations to include more reactor models previously not studied for this project.
Hi, I'm Jonah Cullen, and for my side of the project, I focused on background removal via machine learning classification. While background radiation is typically subtracted out directly from the total energy spectrum, this project investigates point-by-point removal of the background data from the time series data. This could provide a more nuanced background removal, which could improve information quality for spectral analysis, as well as providing a unique data set not otherwise achievable. The data was collected by irradiating an iron foil with an ambi source and placing the irradiated foil on an HPGE detector to collect energy counts as time series data. This data has non-constant time intervals due to the fact that the data is created when an event is registered in the detector. For this reason, the spacing between the data points was chosen as the features for the model to act on. Energy was excluded as a feature, and only the rhythm of the data, so to speak, was used for classification. 4 features were chosen for each data point, being the delta time between that point and 4 other points as shown in the figure. Here we can see 2D and 3D representations of the 4D feature space. We want to separate the anomalies, which in this case are the source radiation events, from the normal data, which is the background radiation. To do this, a one-class support vector machine was used. Due to a lack of known data labels, the calculated expected number of anomalies was used as a target for adjusting the hyperparameters until this number was approximately reached. The impact that this work could have in the field is the generation of a unique data set of background filtered time series data, as well as a more nuanced background removal process that could lend more data points to the final analysis. The future work of this project could include the inclusion of the dead time of the detector, as well as the use of actual background data rather than the cobalt foil data that was used. A planned internship with Lawrence Berkeley National Lab is planned for the summer as well. Thank you for your time.